realized that he will not be able to share the food, so he started already. And as you know, it's 9:30 in Italy, where Mark is. But he's going to join us via Skype. So welcome to the Stanford Robotics Seminar. Yes, it's a pleasure to have you. We wish you were here with us. So I think we're going to place you somewhere where we can, yeah.
You can see that.
Yeah.
Okay.
So it's really wonderful to have this turnout and to realize that how many people are involved and interested in robotics at Stanford. And I'm really, really happy to see all of us, and also to have this opportunity to see what is going on in different laboratories. This was an idea, actually, we started a long time ago. Mark, when he joined Stanford long time ago, I remember, proposed this idea, and we started a seminar at the time. But it lasted for maybe 1 year, and then somehow that was suspended, and now we're starting again, I think, with more groups and more energy, and more people can sustain this effort. So really this happened because of those coordinators here. From each of the group, we have one coordinator who really contributed to putting this together. So I would like these coordinators to stand up. And Margaret, thank you so much for organizing this. So you have a task to just maintain it and keep it going. I think we are going to have this every other week, but from time to time we will have a special presentation by a lecturer, some visitor who's coming to Stanford, an opportunity. So the second week is always could be used as well, and we will make announcement. On the 26th, actually, there will be a special lecture. It will be added to the schedule, which is here. So today's schedule, this is the schedule today, which involves 3 talks and 3 short presentations. So this is, if you remember, in IROS we have the interactive presentation. Very quickly you present, and later you might have a demo to show. So we will have the 3 talks and 3 presentations, and I'm going to ask Emil here to share that first session. So Emil, you keep the time and you run the session. Thank you. Where's my computer?
Okay, thanks very much, guys. So it's great to be here and to kick off the inaugural Stanford Robotics Seminar. So I'm Troy Advar, Zan Majevic, crouched on the floor. So we're from Alison Oak Morris Labs, we're PhD students in her lab. And so we're going to tell you a bit about an overall project in our lab called needle sparing that we both work on, and we'll both spend a part of the time talking about what specifically we're working on. So let's start off with a cheesy crowd survey. How many people have had a needle in this crowd? People have had a needle. Yeah, had blood drawn or had an injection. They just have with anything. Andrew steroids count, so you can put up your hand. So needles are extremely common. They're in all different forms of medical practice. So we have this sort of generic image of what they are, which is a short little straight needle that's inserted to draw blood or give a drug. But in fact, they're used all over medicine. So Example procedures are biopsy if you need to take a sample of tissue even deep within the body to determine if you have a disease, brachytherapy depositing seeds, and ablation if you have cancer, killing it with access to the body. So just so you guys have an image of the type of needles that we're working with, I'm just going to go really quickly through 2 example procedures. So, sorry, it's pretty graphic. Very graphic. So prostate brachytherapy. Prostate cancer is probably the most, I think it's the most common cancer among North American men, apart from some skin cancers. So it's a very common disease. One of the most common treatment options is having these small radioactive seeds inserted around the cancer according to a treatment plan under medical image guidance. You can see here this is an ultrasound transducer in order to kill just the cancer but avoid all the sensitive tissue that's right there. So they use needles like this that have seeds in them. They insert the needles and retract them to leave the seeds. If you have certain types of liver cancer, one of the treatment options is to take long needles, to go deep into the body, and target the tip of the needle so that you're just at the point of the cancer. Again, it's going to be under some kind of medical image guidance, and then you heat up the cancer itself in order to kill the cancer, but again, you're sparing the overall tissue. So those are just 2 examples of a different type of needle, maybe that the rest of you haven't been exposed to. So the overall idea of needle steering as a project is basically this. So if you want to take a needle and insert it towards a target within the body, if you're using conventional straight needles, you're going to have to go along a straight line path from your insertion point to your target. And that can be pretty limiting for a number of reasons. The main one is that you might have some obstacles in the way that you can't hit. So you might have vessels, sensitive structures, and then the other one is that you can only do one path. You can only go along that straight line. So in a nutshell, the idea of robotic needle steering is that you can go along a curved path with a needle using a robotic system.
So our group uses a needle steering technique which employs the use of steerable, tip asymmetric steerable needles. So these needles will have either a bevel or a pre-bend on the tip, and as we insert the needle into tissue, the needle will start to bend in the direction of asymmetry. And if we were to rotate the needle about the base, then the needle can start to bend in another direction. And this is what enables us to steer the needles in curved paths. And just to note, we can model these systems as a non-Hollow cube cycle model that's extended to 3D. So over the last several years, we've developed various needle steering robots for doing this needle steering technology, using needle steering technology. And we've also developed a real-time control system using video images from a stereo display in order to control the needle. And we have also developed pre-operative model-based plans for steerable needles, which we can optimize the likelihood of reaching a target using stochastic roadmaps. And finally, we're also interested in how the needle will interact with our patient, and so we've developed mechanics-based needle tissue interaction models, and we've also, oh sorry, this didn't show up. There's a figure in a paper that you can look up later, but that is using insertion and rotation of the needle while it's already in tissue. If we look at the force data, then we might be able to predict the needle property or the tissue properties. And then we've also done extensive experiments in biological tissue, looking at kidney tissue, kidney, liver, and prostate. And we also conducted what I think is the first and maybe still the only needle steering experiment using a lighting. So all of this work certainly helps to push needle steering closer to clinical use. It addresses all issues that we need to consider before we can actually bring this into the clinic. However, there's still a few more issues that we need to address, specifically issues related to a human operator interface that's more intuitive for the user, and then also imaging and segmenting the needle using medical images, whereas before we were using just regular video cameras. So I'll talk about the first part and Charlie will talk about the second. So the goal of my project currently is to allow surgeon operators to control steerable needles more effectively and more intuitively. And I'm going to play for you to motivate this a little bit, one of my favorite videos. And I'll just let this play for a second. So what we have here is a driver in his car. He's steering what is a non-Hollow system, and he's trying to parallel park this car. And what I mentioned earlier is our steerable needles, they're non-Hollow systems too, and they're very hard to control. So now imagine that you're trying to parallel park your car, but it's not 2D anymore, it's 3D. And so that's an even more difficult task. And so that's sort of the issue we're trying to address. How can we make this more intuitive? That's no problem. Okay, so maybe we should. Okay, so for here, it's fine. Currently, when you control these steerable needles, you're controlling the input degrees of freedom for the needle, which is insertion And additionally, the user needs to have a mental model of the needle kinematics in order to plan paths. And there's a chance that the user will have a wrong model and they'll plan a path where they miss the target, and then they need to update the kinematic model, retract the needle, and try again. So this is what we want to avoid. And so instead, we are proposing a Cartesian-based teleoperation algorithm where the user controls the tip of the needle directly, not the base of the needle, the tip of the needle. And so we have a Cartesian space control algorithm where basically we iteratively plan constant curvature paths for the needle, and we're using a haptic omni to give us the desired position, and we can steer needles much more intuitively. Additionally, with this method, we can give the user force feedback, either force feedback based on how far ahead they are of the needle, or if the user tries to go into a region which is not reachable due to the needle kinematic constraints, we can push the user out of that region. So we've implemented the simulation of the teleoperation algorithms using a phantom omni and Chai 3D, and we're mapping, in the Cartesian space control case, we're mapping stylus position in 2D plane to the desired needle tip position. And for joint space control, we map the stylus orientation about the gimbal angle of the final gimbal angle to needle orientation, and then stylus insertion to our simulated needle insertion velocity. And because we have a kinematic model of the needle, we can use these as inputs to the kinematic model for simulation purposes. Okay, so we evaluated our methods using a human subject experiment, and basically the users steered needles to one of 7 targets here using the 3 different methods of joint control, Cartesian control, and Cartesian control with force feedback. And we asked users to move 2 targets as quickly and accurately as possible, and with as smooth of a trajectory as they could. And we evaluated each of these trials for things like error, how long it took to get to the target, the smoothness of the trajectory, and correlation between the user desired trajectory and the needle trajectory. So we can see that with our Cartesian control method, we can reach targets much faster with straighter paths and more accurately. And then also by adding force feedback with the Cartesian space control, you can see here that the correlation between the user desired trajectory and the needle is much closer together, meaning that there's better tracking throughout the trial using this method. So, since these experiments, we've extended our algorithm to 3D, and thanks to some students in Salisbury's lab, we have a really nice stereo display now for 3D needle steering. And right now we're just working on integrating this with a needle robot so you can steer a real physical needle. But in order to make all of this happen, we need to know where the needle is in tissue, and that will be a good transition for Troy to come back and talk about that.
Okay, so a real simple idea of what my project is about. So if you have a mobile robot or some sort of robotic manipulator and you want to steer it to a needle, you're going to do closed loop control, probably with some sort of optical camera or some other sensor. But when you're trying to steer a needle or some sort of interventional robot to a point within a solid organ, you can't use that idea. You have to use some sort of medical imaging for that position feedback. And that's basically what my project is about, using ultrasound imaging as the position feedback to control a robot. So you can split down that idea into sort of 3 main technical ideas. So first you have to segment out the needle from the ultrasound data. So you have to recognize the position and configuration of the needle from the ultrasound data. Then you have to register that position information, so interpret where it is in relation to the robot. And then you have to implement some sort of control algorithm so you can actually control the needle or some other tool to go where you want it to go within the patient. So I know there are some other people here who work in medical robotics, but I think there are lots of people who don't. So just real quickly, ultrasound is a medical imaging modality. I think a lot of people have the image of it where it's used to take a picture of a baby to make sure that everything's okay with the baby before it's born. But it's actually, just like needles, it's something that's used all over medicine. It's extremely common, it's cheap, it's fast, it doesn't expose the patient to any radiation. And the most common type of ultrasound is B-mode imaging. What that basically is you have a whole bunch of transducer elements. They send out this ultrasonic wave, and then you really just listen for the reflections to come back. And depending on how long it takes them to come back and how strong the reflections are, put a brightness at a depth. And that's what this image is, brightness image. The other common type, or another type of ultrasound imaging is Doppler imaging, and that's what I'm using in my work right now. So here you have the same B-mode image, but on top of it you're showing this color. And what that indicates is the frequency shift in the transmitted wave, which just like when you hear an ambulance going by, the sound sounds different because of the frequency shift. you can look at the frequency of the pulses you get back and use that to interpret velocity. So it's used a lot to identify problems with blood flow, looking at vessels, but we're actually using it to look at vibration and velocity of solid targets. So because we're interested in 3D needle steering, like the title of the talk, we're using 3D ultrasound. And what our system is we've got this transducer. It's got a 2D image. So you can see this is a cutaway image of this. It's a slice through the phantom. This is a simulated tissue. And then our transducer just rocks that image back and forth. So you get 2D images at discrete angular intervals, and that gives you 3D data in a volume like this with films up slices. Okay, so why, if you can take 3D data like this of a tissue with a needle in it, why is it a hard problem at all to be able to automatically segment it out? It is a really hard problem. It's been talked about a lot in the research literature, automatic needle segmentation from ultrasound images. And it's hard if you have a straight needle and you're taking 2D images. Just because if you have an angle between the ultrasound, you're going to have sound waves bouncing all over the place. Your imaging plane might not even contain the needle because you're talking about very thin planes. And you can have tons of artifacts. And we'll show you examples of all these in the next slide. There's lots of other reasons, particularly when you start talking about curved needles and 3D data sets, but we won't go into those. So this is, if you had a needle, a straight needle that's going straight into the screen, this is sort of like the best case image you can get. This is just that phantom. There's nothing else going on in there. This is sort of just empty space in ultrasound. And that little dot right there is the cross-section of the needle. It's a very specific little dot. You can pick it out pretty easily as a computer vision problem. This is with the imaging plane perpendicular to the needle, so it's straight right on the normal. We tilt it about 5 degrees. You can see it gets harder to see it. It's not as easy to identify the dot compared to the surroundings. And then if you go just a few more degrees further, you can't see it at all. So the needle is still in roughly the same position, but your angle is just about 5 degrees higher here. So if you're taking that imaging plane and you're sweeping it over a needle, you can imagine reconstructing this shape is really hard because you can't see any images. This is a different configuration. Here the needle is going across in the same plane as the image. But this is a straight needle, and it's just a tiny little bit out of the ultrasound plane. And again, you can't really see it. It's difficult to do the line detection because you're going to have gaps. And if you have a really curved needle, that problem's going to be even worse. And here, these are those two types of images, again, showing you some common artifacts. You can have blurring, you can have all kinds of problems going on where it's not easy to pick out a clean needle shape. Okay, so our solution is to use that second type of ultrasound imaging, which is the Doppler imaging. So we use a mechanical transducer, we vibrate the needle at its base outside the patient, and then we use this Doppler imaging, which is optimized for picking up blood flow, to pick up the vibration of the needle all along, so the vibration of the needle and the tissue around it. We do that in the 2D slices like I was talking about. We detect the needle cross-section across a bunch of slices, and then we just fit a polynomial curve or some other type of curve through the resulting points, and we use that to reconstruct the shape of the needle in 3D. And the great thing about this is that it's not sensitive to angle, and it, well, that's the greatest thing. Okay, so here's the, a 2D image of the Doppler image. So we've got this color is what you get from the Doppler. So that says that there's some velocity in there, just like those images of blood flow. This is power Doppler, so it doesn't show directions, it's just one color, it's like intensity. And that cross star right there is just at the centroid of the Doppler response, so the integrated centroid of the Doppler response. And that is all the image processing you need to do to pick out the cross-section of the needle in these images. And just look at that color data alone, you find the centroid of it, it's extremely quick, and then you have the position of the needle in 2D, you combine that over a bunch of slices, and you have the position of the needle in 3D like this. So this is again, we're just looking for the centroid of this power Doppler data. You can kind of see that blue cross there. And we're building up the cross-section. So this 2D image is sweeping up along this, and we're building up the cross-section in 3D. And in this image, we're looking down on the needle from over top. So the frame rate of the ultrasound is actually a little bit faster than this, and basically we can process each image as soon as we get it in real time. Comparing that automatic segmentation to a really careful manual segmentation where we go through and manually find the data points, we found that you can reconstruct just with that polynomial fit, that was a third-order polynomial that we were showing, so that it's accurate to within about 1 or 2 millimeters. The average error is somewhere about 1 millimeter. And that's true across a range of tissue stimulants. It's true for different vibration frequencies, and it's true for different parameters of the imaging. So it's not super sensitive to any of those, and it lets you really quickly get the shape. So now that basically gives us a method for reconstructing the shape of the needle quickly, and now we're looking to apply that in closer control of the needle. So that's what I'm working on right now. We had a couple of rotating students, Ashley Fletcher and Tao Zhang, worked on building a new needle steering robot by modifying an old one. So now it can run directly off our ultrasound console, so we can process the data, control the robot, and do the whole thing closed loop. And that's what we're looking at next. And so to sort of tie together what Anna and I have been working on, like a future vision of needle steering, we have this needle steering robot It's performing operations with ultrasound guidance, but in coordination with getting input from a human clinician. The whole thing is being done in closed loop, and there's a possibility to implement new technologies for diagnosis or treatment, and overall just give a new clinical tool that really doesn't exist today in medicine. So with that, we'll wrap up, and thank you very much.
What frequency are you oscillating the needle?
So somewhere between about 400 hertz and about 12 hertz. And the displacement is really small, so it's like less than 10 milliseconds.
How long is the needle?
So the sweeps that we were showing right there, we were doing it in the phantom tissue, and it's probably about like that, a few centimeters, 10 centimeters, something like that. But I think that you can do it with much deeper phantoms, and the same basic idea applies. And when you're doing the deep, if you're looking at an organ, that's when you're going to really get some larger angles, depending on the configuration, and that's when you really need the sensitivity.
In the animal study, the insertion is made 5 maybe 10 centimeters for different.
Cool. Okay, we were pretty long. Thanks very much.
So now we will do 5 minutes before, and from our participants, learn more and something like over their paper.
Hi, my name is Jongha. I'm working in BDML with Santi. And today I'd like to start my presentation with this. Imagine your doctor can feel the texture and stiffness of your organ without touching it actually. For patient, haptic and tactile information is key to succeed the delicate intervention. However, many teleoperation systems has a difficulty to deliver those information, even though it helps patients a lot. So our system hopes to change that. Our needle can make you be able to feel the grains of the sandpaper by scraping on the needle tip. So, and it's also MR compatible, so it can work under harsh magnetic environment as well. To build the haptic feedback system, we designed for sensing needle using a fiber break grading sensor, which is known as FEG sensor. The sensors are embedded along the needle and its tip. The last FEG sensor can measure the force at the tip by reading the wavelength change. However, there was a problem. With the ordinary plain needle, it shows a very insensitive to the axial road. So we need to increase the axial sensitivity by placing the many small holes around the tip region. By doing this, we can improve the axial sensitivity by 200%. We tested our design with FEA tool like that, and we manufactured it. With that needle, we conduct several tests to characterize our force sensing needle's ability. It can read minimum 4 millinewton radial force, and it can read 8 millinewton axial force. It shows the wavelength change of FEG sensor is linear to the load we applied, and it also shows flat frequency response up to 200 Hz. We compared our force sensing needle and commercial force sensor, ATI Nano 70. The red line shows the ATI data. As you can see, there is a clear difference, especially when you closely look the moment when it punctures through the membrane. The ATI affects by inertia. So you can see the reverse direction of it. But but while it shows the inertia effect, also our system has no inertia effect. Also, there is a force from the friction between the tissue and needle. So you can see the gradual change, gradual increase in the red line, but our system has immune to the frictional force. So you can discriminate a small change in the tip force. So our needle has several benefits over the commercial force sensor. It is MR compatible and sterilizable, and also it's immune to the frictional force and frictional effect and inertia effect. So you can discriminate a small change in the tip force. We built a 1 degree of freedom haptic feedback system with this needle, and we are trying to compare two different modes, which one is based on our force sensing needle, and one is based on the commercial force sensor. There's a clear difference, and there is a short clip. To explain what our system, haptic feedback system is. You can see the handle in the user side is formed by the force at the needle. So we bring our force haptic feedback system here, and it will be a really cool experience if you really try it. So I hope you to try it here. And is there anyone to try first?
We have some phantoms here. So as Jungwoo explained, there's a sensor, an external sensor at the base of the needle, and then there's our optical base sensors at the tip. So if you normally, when you put a tool on a robot, it has force sensors at its wrist, but you can't really tell what's going on at the very tip. And we have some interesting different phantoms here. This one has little vessels in it, and it's a plastisol material, so you can feel going through the plastic, and there's a lot of friction that actually starts to build up, and you will feel from the external sensor that you don't really feel from the from the FPG sensors. Yeah. She won't tell you which feedback it is. And then so that's a voice coil. Repurposed speaker. So you can let it keep your fingers and
How you feel? How you feel?
It's difficult to explain.
yeah, don't push it in because it's giving you feedback.
Oh, okay, yeah. Make some noise.
Oh, here. These are you won't be able to feel What do you feel?
No, I can definitely feel it. It's very crisp. Very crisp feeling, yeah, I like it.
Okay, so what is good is that everyone could try it later.
Yeah.
We will check out,
Thanks.
Thank you very much.
So I'm going to bring you on a quick tour on what we've been doing recently in haptic simulation. But before this, for those of you who are not too familiar with haptics, if you first think about just how we interact with machines every day, we're using computers, you may be using a coffee machine. We typically use, to interact with the machine, maybe a switch, maybe a keyboard, a mouse, and that generally covers about 90% of the way we interact with machines. In return, depending on what machine you're interacting, you might have a little LED that will light up, could be a little dial, maybe a screen with some imaging, could be something, full 3D image if you're working maybe with an imaging device. And that generally works quite well, except that if I tell you to bike home today or drive home using a mouse or a keyboard, that becomes kind of a much more challenging problem. And driving a car today, well, we still use, we use a wheel, and unless you maybe have one of those Google cars where you can just click on the map and the car will drive you there, you still need this kind of really crude interaction with the wheels. You need to feel the car, you need this kind of very fast interaction between the directions of the wheels. You may want to feel that the wheels are spinning. And that introduces this whole notion of feeling the physics, feeling the physical interaction. So the question we've had is that, well, if we're looking at physical interaction, we're looking at introducing the sense of touch, and the idea is that, well, could we actually use the sense of touch to actually start developing some digital applications where you're not just going to be using maybe a mouse or a keyboard, which can sometimes be really tricky if you're doing some CAD design, but can you really just have your hands go into the computer and start manipulating objects? So to show you this, to demonstrate this, we're going to take an application that's actually quite tricky, where you really need your sense of touch, which is some very fine assembly. And actually here you actually have a watchmaker who's using all the skills to insert the fine little wheels, mechanical parts, and try to form this. So imagine that we take this idea, and we're going to try to build a simulator. And we're going to try to duplicate what this watchmaker is doing. So obviously we're going to need a number of things. Starting off, a device which will allow us to actually render those forces. We're going to render graphics. We want to render those interactions. And what those haptic devices are, for those who've never tried one, it's basically a small robot with a set of motors and sensors. And we can track the position and orientation of our hand. We may have different tools at the end effector, and we have some motors that can recreate those forces. On the simulation side, we're going to have some models. What we like using in computer graphics are triangles. Those are our bricks that we're going to assemble together to kind of create those complex models. The next step is going to be collision detection. We need to really compute the physics, how those parts are colliding together, what are the distances. And from that, we're going to be computing the forces. This is what we call haptic rendering. And as we're going to compute those forces, the idea is to send those forces back to the device, and hopefully we'll create the illusion. So just to show you, in terms of haptic rendering, what we look at, well, first of all, we start from the haptic device. And we are reading the position to the computer, and I'm going to be updating a small cursor over there. Just to give you an idea of speeds and the challenges is that to get a good animation, we're rendering about 20 to 50 frames a second. For the haptics, we need about 1,000 update rates a second. So 1,000 times a second, we're going to read the position and send the forces. And 1,000 times a second, that means we have to do things quite fast. And you'll see why in a moment it becomes critical. The next step is, how do you render forces? Well, obviously, if I'm in free space, nothing to worry about. Let's say 0 forces. As we come in contact with the surface, we now need to figure out what force are we going to send. And we've got one challenge here. We've got this cursor, just like our finger comes on the surface of the table, and ideally I'm going to press. My finger should stay at the top on the surface. We've got a haptic device with limited force capabilities. We can maybe render 5 to 10 newtons on a device, but eventually we can push through and really push the device down, which is exactly what I'm going to do there. So if I push down, well, what's happened is that little white ball, this is actually where I'm located in space. This is the little gray ball is where I would like my finger to be. And what we developed back in the past in the lab was this concept of a proxy, which is this ideal finger moving around, and the real position of the device, so finger proxy. So here you really see it moving around. And what we have a virtual spring that pulls the device back towards the cursor, the proxy. Now, with this, well, here you see moving on the surface, We can add all kinds of effects. Playing with how the cursor is going to move, you're going to be able to add friction. And some of you have probably heard the notion of a cone of friction. Well, there you're actually going to see it. So here I'm actually moving my device, my cursor is not moving, and suddenly I move sideways, and you really see this cone of friction. What I'm actually feeling is the friction as a resulting of this. And actually here, if I come down here, you can even use static friction, you're going to see how the little sphere can change. So that's all very simple, and that's to give you a flavor of what we do with a single point contact. Obviously, we want to go one step further, which is there we go. So we obviously want to have full 3D objects, and this means we're going to have a whole number of collisions. What we want to do is to go from an object like this and to perform a real insertion. If you look over here, you're going to see a number of those little contact points. And as we're going to approach, we're going to take those contact points, and we're actually going to use the same idea of a virtual spring that's kind of pulling the object towards you. And we're going to try to minimize the distance so that we're going to perform a perfect fitting. To do this, well, we need to solve this problem of collision detection. There's a lot of work in computational geometry to do this. What we did is to revisit this field and use untapped power coming from the graphic cards. You've got today on a graphic card, several hundred to even several thousand cores, and we've parallelized those algorithms so that we can really leverage this power. The whole idea of collision detection is to take two objects and to figure out which points, which polygons are in contact. So if you have an object made out of 10,000 to 100,000 polygons, and a second object with the same number of polygons, if you're going to compare every single triangle, the problem is going to explode. And keep in mind that you have to do this at 1 millisecond. So there are a number of techniques using bounding boxes where you look at, for instance, you wrap up those objects with bounding boxes, compare the bounding boxes. If they're not colliding, no need to go any further. And as you kind of go down, you're going to figure out which are the triangles interacting together. When you run this on a GPU today, you can pretty much speed up the whole process from 50 up to 100 times. So now let's see what's the result. So what we're going to do is we're going to actually load in a few parts of a watch. We're going to load in a few gears. And I'm actually going to go over there. And we're going to take this here. The first thing I'm going to show you are those contact points. Let's rotate this here. And as I approach, we're going to actually start seeing those contact points. You see those little distances? What I've decided to do, because I'm rendering graphically, I'm going to say to my system, well, tell me when those parts reach a certain epsilon. Here maybe I have half a centimeter. As those parts approach, we're going to highlight those points. And as you move around, well, you kind of see those points changing, constantly changing. If parts intersect, well, here we're highlighting the objects in red. Now what we want to do with haptics is we're going to reduce this epsilon to a tiny distance, so that when the parts reach maybe a hundredth of a millimeter, we're going to consider this as a contact point. And this is what I'm going to do now. I'm going to turn on the haptics, and now, as I'm coming in contact with those parts, I'm computing the contact points, and I'm going to adjust the position of the parts according to where I am. So now let's take a look. If we start taking, for instance, those two gears, we'll move this one over here, and here we are. Now I'm in contact just around here, and if I rotate it, if I move it around, you see how the contact points now are kind of orienting, constraining my field. Obviously, if you really want to assemble it the way it should be, rotate this, and there we go. It's called full assembly, and all the contact points are respected. We can do this because we're using the GPU. We can actually go way more. We can have way more parts. So one of those watches can easily have about 100 parts, depending on the complexity. And this one, and this one, for instance, a little tricky one. You have to take it here, so you can see. So I'm going to kind of insert it in there, and just using the haptic feedback can very gracefully insert it. Which is a really challenge when you're using CAD tools. You kind of have to say where you're going, find the constraint, click, and eventually you will get there. So this is for our tool. And the next step we want to do is, well, let's add some dynamics. We do a lot of work with robotics, but we want those parts to move around. We want those objects to collide. So what we're going to look at is, well, how are those bodies colliding? But really what we're interested in is how we're going to model the dynamics. And some of you who've done some simulation today, you may download one of those ODE or graphic dynamic engines that are used typically in games. And the way games typically do is that you have a whole number of objects, free space, things are shooting around, boxes are colliding. But if you start linking those objects together to build a robot, what you have to do is add constraints. And adding constraints basically means that I can take two bodies, two that I can move in 3D space, and I'm going to say, well, I'm adding a constraint here so that it can maybe only rotate around a certain joint. If you look at how those problems are solved, well, every constraint you're going to add is suddenly a big matrix that you're going to have to solve. And the more of those degrees of freedom you're going to be adding, the more difficult the problem. And also, you're going to get all kinds of numerical issues as you're trying to solve this. I mean, the truth is that you're never going to compute the exact solution. And depending on how ill-conditioned your simulation could become with objects that are flying around, you have to address this. So what we did in the lab was to kind of rethink this and to really go from our whole idea of how do we going to model a robot, and to really say, well, if we've got a robot with 6 or 7 degrees of freedom, we're going to represent those robots with those exact degrees of freedom. And as we're going to be computing those collisions, we're going to see where those forces impact at the exact location, and then propagate those forces down through the end of the robot. And that allows us actually to really simplify the problem. So I'll just show you kind of the end result of this. Here we have 2 KUKA robots, which is exactly the one we have over there. And the way we like developing our software is to actually test our controllers in simulation, and then we simply switch over to the real robot. So here, I'm actually going to use again the haptic device to interact with my environment, and I'm going to actually take control of one of my robots. Take control of the second one here, and you're going to see how now by simulating the dynamics and the collisions in real time, got a very interactive system. Objects in the environment, interact with them, and so on. So this is kind of our core framework for simulation. And where we're going with this? Well, we're looking at a number of problems. In the lab, we have a number of robots, including the orange robot, the KUKA robot. We are working with Asimo. Asimo is it's a pretty complicated robot, and developing on it takes time. So using those simulation tools are extremely useful, especially when you can simulate contact, you can simulate friction between the robot and the environment. And some of the more recent project we're working on is on an underwater robot. And this is a big project with Power State University, where we're developing basically a bimanual haptic workstation to actually control a robot under the water. And the whole idea is to come up with some really intuitive way of controlling the robot, and to let the operator just focus on the task, control those grippers, and using a stereo display, being able to interact with the environment. And we've just begun with setting up the workstation now. Eduardo is working on the design of the robot, Gerald on the control, and we hopefully will start going in the Olympic swimming pool at Stanford sometime this summer.
Watch for robot.
Okay, that concludes the presentation. Thank you.
Okay, thank you. Let me get this set up here real quick, and then we can get started. So it's kind of a blessing and a curse going after Francois, because he gave a really good introduction to haptics, but he also has a really cool simulation. So what I have here is just a 1 degree of freedom demo, but hopefully it demonstrates the concepts that I'll be talking about. So I'm working in model-mediated teleoperation for control of robots in outer space. So like Francois said, for haptic feedback, he's trying to run at a kilohertz to give good feedback. Well, when we're trying to control a robot in space, it takes about 1.5 seconds in really good conditions to get a signal to our robot in outer space, and about 1.5 seconds to get that signal back. So what we developed, and I'm going to show today, is just a little small 1 degree of freedom demo that we've been using to test some of our ideas of model-mediated teleoperation. And I'm going to use this demo just to kind of talk about what we're doing. So what we have up on the big screen here is our user interface. So I can move this haptic device here, and it'll move my arm that is constrained to 1 degree of freedom. And that's what the person would see. And then what you see on this screen here is our robot in outer space. So I can put on a time delay. If I can find my cursor, there it is. And what you see is this is like a video feed you'd be getting back from outer space. So I move this, and about 3 seconds later, this one, I'm assuming, can't see, but good. So it's working. So instead of interacting, like Francois said, where we have this virtual coupling, this virtual spring between our haptic device and our real robot, if we did that with this 3-second delay, our haptic feedback would either be unstable or meaningless, one of the two. So instead what we do is we use a local model of our device. So I have this local model of our robot arm that I can move back and forth. And the haptic interaction is actually, we have this haptic device here coupled with a virtual spring to that virtual robot. And so in addition to having a virtual environment that we interact with in terms of the robot, we actually build a virtual environment of the true environment in space. And one of the advantages is, for our application, we're looking at repairing satellites. And so we have CAD models, we have material properties for all the satellites in space. So essentially we have models already that we can use for rendering. What we've been looking at, so there's this idea of model-mediated teleoperation where I maintain stability in spite of this time delay because I only interact with this model. And I update this model based on sensor feedback in such a way that I don't cause instability. And how you do that, we're still working on it, and it's still a little bit debated. But one thing we're adding to that now is a predictive model of our environment. So traditionally what you do with model-mediated teleoperation is you would just have, you would get your sensor data and you would display a virtual environment. But what we're doing now is we're taking that sensor data and we're going to predict, in our case where we have 3 seconds of time delay, 3 seconds into the future where that environment is going to be. And you're actually going to be interacting with that prediction. And what that enables you to do is interact with dynamic environments. So, for instance, if I try to catch this little satellite that's going to be coming in here from the left, I don't even see it yet. I can try to guess, right, where it's going to be after the time delay, but you can see I didn't do a very good job guessing because of this 3-second delay. So what we're doing is I can turn on our predictive control, and when that pod comes in, I can interact directly with the object. I can feel haptic feedback in it. And what you see is that in the remote and out in outer space, the robot's doing the exact same thing. Yeah. And in a minute here, I'll let somebody else come up here and give it a try. So you can see I push on it here, and then 3 seconds later when I get the data back from outer space, I see that the virtual robot is actually pushing on it. And normally we have these two screens side by side so the operator can see both the delayed feedback and this predictive feedback. So if somebody wants to come up here and give it a try, we'll start with haptic feedback off. So we have a volunteer who wants to come up and give us a try real quick. I think we have time, right? Yeah. Anyone? Yeah? Somebody? Come on.
Come on, guys.
Yeah? Okay.
I would, but I have this before.
You don't know how you can do that properly. You're a ringer.
So what we're going to do first is we'll let you try it without haptic feedback. And what I want you to do is I want you to contact the object at the beginning of that green cylinder and then try to stop it at the other end. And it's, yeah, you can sit on in the chair if you want. And be nice to her. It's very hard to do it the first time. So there's no time delay here. And you just want to kind of cushion it in. Yeah, so it's pretty hard to get the hang of it first. And the challenge is right now it's 1 degree for you can't grab you cannot grab the object. So all you can do is push on it. So here I'll turn on haptic feedback. And so now you'll be able to feel how hard you're pushing against the object. Okay. So it takes a little bit of...
Feel the stiffness and like
Yeah.
as you're pushing against it.
Here, I'll give you one more try on this. So you kind of have to, cushion it, and then since you can't hold it, you have to take off the force right when it stops. So just pull that. Yeah, much better. Okay, so now we'll try with the time delay on. So now there's 3 seconds of delay. Unfortunately, you won't be able to see the full delayed image, but so you can kind of try to guess where the object's going to be in 3 seconds and try to cushion it in. Good luck. Right, she didn't even touch it before the real robot had already pushed it away. So it's very difficult. So now we'll turn on our predictive display and see how well you can do it. So it's much more like interacting with it with no time delay. Essentially, we're eliminating the time delay. And it's a little bit overly easy right now because we have not a real environment, but a simulated real environment. And so our model of the environment in this case is perfect. But what we're looking at now is we're going to be doing a human study where we vary the modeling accuracy between our simulated environment and our real environment and see how operators are able to compensate for those errors. So thanks for your time. And if anybody would like to try this after we're done, I'd be happy to let you try it. Thanks.
Great.
So our last talk is there 15 minutes given by Paul. He's working with markups.
Hi everyone, my name is Paul Garples. I work with Mark in the BDML on interactuated robotic hands with Hannah Stewart and also Dan Hawks. So thanks a lot for your time. I will be talking about a robust robotic hand design for an exemplary baby robot, so switching to more hardware-related things. So first I'd like to give you a little bit of an introduction on the DARPA Robotics Challenge. This is what the hand is for. Many of you have probably heard of this challenge, but in case you haven't, it's being put on by DARPA, and you can see the goal there. It's, I'll just read it to you. Will help develop robotic technology for disaster relief operations. This technology will improve the performance of robots that operate in the rough terrain and austere conditions characteristic of disasters and use vehicles and tools commonly available in populated areas. So you can see that pretty much summarizes all the main goals. It was partly or primarily inspired by Fukushima. There were some robots available for that, but the response was not what people were hoping, and people thought that with the robotic technology as mature as it is, there's a lot of room for improvement. So there's a lot of funding going into this challenge. The challenge also, I should mention, is this December, so it's coming up pretty quickly. These are the tasks that are part of the competition. So drive a utility vehicle. It's kind of like a Superman sort of robot competition. Climb a ladder, traverse rubble. So you can see there's sort of an illustration of what the robots have to do. Open a door, break down a wall, identify a leaking pipe, close a valve, and attach a connector. So I'm working with JPL, who is building a robot for the competition. It's called RoboSimian, after its ape-like shape on the top right. That's an artistic rendering. JPL contracted Mark's lab, the BDML, to build a robotic hand because of their extensive experience with interactuated hand design. And you can see a picture of the current CAD of the arm as it stands. Just for scale, it's kind of hard to tell from these pictures, but that arm is about 2.5 feet long. So it's quite long. The guiding principles of the robot, as outlined by JPL, are slow is smooth and smooth is fast. So quasi-static cases, 3 points of contact on the ground at any given time, slow movement of the arm, as little dynamics as possible, and as stationary and as stable grasping and operations with the environment as is allowed. Also, they're hoping to, the competition, some of you may know, but like the Robonaut is one of the competitors. There are several other ones who are farther along in the technology. So JPL is starting out almost entirely from scratch, but with some hardware already developed, but very little. So they're targeting early field development, and serviceability and repair in the field is going to be really important for the competition. Also, they're trying to standardize parts, so the different segments of the limb that they're designing are going to be interchangeable so that you can do serviceability in the field. Okay, so now onto the robotic hand, which is my project. You can see some renderings here of the hand as it stands. Some of the design goals for the hand are the robot will actually walk on the palms of the hand, which hasn't been done before. So the hand will need a very robust polyurethane pad in order to cushion the robot. The robot in total is about 100 kilograms. So there's quite a bit of force being transferred through the knuckle, through the palm, and so the palm's going to be strong enough to accommodate that. Also, since the robot needs to be able to interact with human tools, it has to be able to operate the trigger and pistol grips. It needs to be able to turn the key in the ignition, so it'll need to have a pinch grip. It needs to be able to climb the ladder, so have a very strong wrapping grip. And this is actually one of the main drivers for a lot of the design decisions that went into this hand, which is it has to be able to support a 100-kilogram robot, which no robotic hand currently available is able to sustain that strong of a grip. Like the Barrett hand will break above about 10 to 30 kilograms supporting, and so accommodating that, and then also being able to accommodate any overload scenarios is a real challenge. It also needs to be robust to collisions and impacts, so have stops for the fingers so that if you do something like this, that you're not going to damage any phalanxes or any joints, which is a real challenge. So building in compliant stops for different finger segments is a big challenge. Serviceability and simplicity, this is another common theme. So each of the fingers is going to be identical, which means they can be swapped out and exchanged in the case that one of the fingers is damaged or broken. The fingers are going to be under-actuated, which some of you may know what that means. That means there's one motor per finger. So there's one tendon that causes the finger to close, and then either springs or another tendon that causes the finger to open. So that leads to a lot of simplicity and nicety in mechanical packaging. And we've also been targeting low cost. This is another main goal of the robotics challenge, is that all the hardware will be mass manufacturable and affordable. Okay, so here's a list of some of the design challenges that I've outlined. It's nowhere near comprehensive, but it just gives you kind of an idea of what the challenge is for the hardware. Shape, packaging are mainly the mechanical constraints, so that's mostly how everything fits together. You want to have a very robust and tightly packaged unit. If you look at a lot of robotic hands that are made in by different universities around the world, the tendons are often exposed. There are joints that are exposed. There are pieces that come out of the back of the hands, which, if those were to get hit against things, then they could snap and break. And so making the packaging as tight as possible is definitely adds to serviceability and the robustness of the hand. For sensors, since it's an under-actuated hand, you have to measure the angular position of each of the knuckles. So that's a challenge, and there are optical, magnetic, and mechanical ways of doing that. So deciding between all of those, measuring pad force and contact force, so you know how tightly you're gripping an object. Measuring the motor current so that you know how, that also is another way of getting feedback, but there's stitching and other mechanical constraints that come into play where you sometimes need both of these forms of force feedback. And then there's electrical constraints. The robot is going to run off of a 200-volt lithium-ion battery, and so that supply needs to be converted to a supply that's usable by small brushed motors that can go into the hand. So getting we're using a Vicor DC-DC converter, which is a small power puck essentially that converts that. So figuring out what the best packaging constraint, the way to do that in the smallest package is a distinct challenge. Also the software for the controller, so there'll be a microcontroller in the hand that does all of the sensor acquisition and motor control, and then also communicates over RS-45 or Ethernet, that's still to be determined, back to the main body of the robot. So now I'd like to look a little bit at the finger design. So you can see the progression sort of from blocky first stage prototypes. This was a test stand that we developed in the lab to test an individual finger. The finger looks very blocky, it has stops on it, but the tendon is shielded. It sort of travels through here, around the pulley, and around another pulley, and gets terminated at the fingertip. And then a second generation, which is laser cut out of masonite. This was 3D printed, so we've been leveraging, since the time schedule for the whole project is that a first version of the hand needs to be delivered by June. We're leveraging rapid prototyping techniques to be able to test the design intricacies and details to make sure that they're going to work. We also built a fully functional hand prototype with big fingers. Here's another picture of it over here. So this was to test, there's polyurethane pads on the fingertips. These are 3D printed finger segments, and then motors in the base. So to test whether this overall configuration is going to work for us. And it seems like it will. There are some differences that in the palm design in particular that we're going to change. And then for the final design, which is what I'm exploring and working on for the next several months, is this cutaway view, which you can also see a more detailed cross-section view of one individual knuckle. So the first thing that you can notice is just how tight the packaging is. So this is, I have pretty big hands, but they're rough. They're a little bit bigger than mine. They're about the size of Wilt Chamberlain's hands. So that sort of gives you an idea of the scale of things. So fitting everything necessary to make robust knuckles that will be able to support the 100-kilogram weight is a real challenge. So in this configuration, we have bearings, the potentiometer sandwiched right there really tightly, then the other segment that fits in the middle with a pulley on it, and then 4mm dowel pin in the middle. And what, let's see, there's a bone structure, as I like to call it, which looks like this, that goes in down the center of the finger, and then there's a polyurethane cover that slips over the top. So using 3D printing, you can very quickly make polyurethane pad molds of various intricate geometries that slip over a shape like this. This is the FDA from SolidWorks to make sure that this shape and this size of aluminum will actually rotate the force of hanging this robot off of the ladder. Here's a picture of the pinch grip, and you can see there's the wires get routed along the side from the potentiometer. Each potentiometer has 2 wires. So looking at the palm now, there's some interesting features of the palm. There's a large polyurethane pad, as I talked about before. The fingers fold back to be protected, and when the robot needs to walk on its palms. There's an ATI force sensor, as is very common in the wrist of the hand. This is an interesting feature that I haven't seen in any other robotic hand, but we decided that a webcam would be really useful for actually viewing what the hand is gripping. So this is a view in SolidWorks of what that webcam actually will see. So you see finger, 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 gripping towards the steering wheel. And this is the webcam. It's an off-the-shelf webcam from Amazon, and it has to be wide angle in order to view all of the fingers. This is a picture of the hand on the actual robotic arm. And here's it's not the greatest picture, but you can see there are small brushed motors, and those are going to drive worm ears that actually have the tendons snake coiled around it. And the reason for using worm ears is so that you can have power off gripping, so it's not back driving. And then this green puck in the base of the palm is the hand control, which I'll talk about next. So this is the hand controller. It has a microcontroller, which is a modern, I think it was released a few months ago, STM32F4. Very nice floating point microcontroller, which has plenty of power for what we need to do. Then there's 3 brushed motor controllers, which are in this area here. Then the DC-DC converter that I talked about before, which is the 200 volt to 24 volt converter, which is a large brick that sits here. Then a row of analog inputs for the knuckle potentiometers, and accelerometer gyro, just because they're really inexpensive these days, you can put them on. And it'll communicate over RS-232 or 485 to the main body. So the goals for the next several months is to shrink this to the size of a hockey puck. And this currently, per scale, is about 7 inches by 3.5 inches. So just future goals and deadlines. The competition is in December, so they need 4 hands by then, and they'd like 1 completed hand by June. So that's sort of the timeline. And thank you very much for your time, and I'd love to take questions.
You mentioned several times that you're designing the palm so the robot can walk on it. I'm just having a little trouble visualizing that. So is the robot doing a handstand, or is the robot going to just have very long monkey arms that's used for balance?
Sort of both. So imagine your fingers folding back and then sort of walking like this on the palm surface of your hand.
So where are the legs then of the robot? Is the robot doing it?
The arms. There are the legs.
Oh, okay.
So it's completely there's
it's
two left hands and 2 right hands,
okay.
And they're all the same.
Okay.
Yes.
So when it's going to be actually operating in the field, it's going to be at each single moment working with just one hand, or how would it balance itself on?
There's been some talk of having it sort of squat down in a pose and then be able to work with 2 hands. For most tasks, JPL is hoping that they can just use 1 hand, so you have 3 points of contact.
Do they have torque control on the arms?
Yes, there are frameless motors and planetaries in each of the joints, and then those will have torque control. They're using Elmo motors.
Again, these potentiometers and knuckle, what if one of them breaks? Is there a backup plan?
Software.
Do you have something in the motor data that can give you an estimate of the finger pose? Or?
Yeah, there are encoders in the motors. And those with the finger pad sensing can give you a backup, but you'll just see that signal rail if they do break, and then you'll be able to swap out the fingers if it's important, or just if the hand still works, then you might just choose to continue operating the task. Yes?
Will you be able to hang from the ceiling like with these fingers strong enough to support this entirely? So if you'd like to again overhead, climb it.
We're designing it for that worst case. I'll let you know when we have the hand and the robot's hanging.